Alright, so the second video here, this is like the 10th time I've tried to record it because every single time something goes wrong, whether it be with the computer or my dogs, who have been making every sound imaginable they can do, whether it be howling or playing or squeaking on something, they keep interrupting and I keep restarting this. So 10th time is a charm. Let's do this. I have some good news for you, and the good news is that you already know how to calculate one of these things, the z obtained. We haven't really called it the z obtained, but the z obtained is just the z-score that you've been calculating these past couple of weeks anyways. The z obtained is going to look something like this, which, you know, will look familiar to you. Or if you're working with a sampling distribution, it might look something maybe a little bit more like this. Right? Where that's the standard error now instead of standard deviation. But that is your z obtained. It is essentially the score that you're going to get to show exactly how far away your new results are from where you thought that they would be. Which, if we backtrack a little bit, that's exactly what this is asking us to examine, right? What we got with our data, what we thought we were going to get, and a measurement of variance, or standard error or standard deviation to help us know how far away those two values are. So the z-critical is then going to be a threshold that we're going to use. So the z-critical is going to be anytime your z obtained exceeds the z-critical, then it means that you can reject your null hypothesis. In other words, what this means, if I try to break this down into plain English, and even if I try to break it down in plain English, it's still kind of complicated. But what this means is that if your z obtained is really, really far away from your z critical, then that means that your z obtained comes from a score that is very, very, very unlikely. So unlikely that it could be that this z obtained represents a separate population. When would we find this? Well, if you're getting a score, let's say that you have some predictions about this new batch of clients that you're working with, and you notice that they seem to have a lot of like really high scores on depression or something like that compared to the folks that you normally get. You would be able to use stats to determine whether or not it is a significant increase compared to previous cohorts and previous clients, because you're going to collect their data, figure out where their data are in comparison to the population by getting the z-score, and then you're going to compare that to the z-critical, which is where essentially you have drawn a line in the sand and you have decided if this z obtained exceeds the z-critical, then this is a very rare thing to happen by chance. Therefore, it may not be happening by chance. What does that mean? It means that these clients are more depressed than you would normally expect in any given year. That's just one example, a really depressing example, but you get the idea. So what we're doing here, the reason, and you're gonna, there'll be figures and illustrations that make this a little bit more clear, but we got our normal distribution right here. Remember those tails, right? That these are the really unlikely areas of the tail. So if you have a z-critical, that's going to be right here. Let's just say, for the sake of argument, this is z plus 2, which means that anything beyond a z-score of 2 that you obtain is going to be a significant effect. This one is going to be beyond a z-score of 2. Let's say it has a 2.3. Therefore, we can reject our null hypothesis. We know something is going on with our data, something interesting is going on with our data, because this is a very unlikely thing to happen just by chance. Therefore, it may not be chance. Alright, so if the z obtained is greater than z critical, then we can reject the null hypothesis. The opposite is true if you're working with negative z criticals, which can be the case. If you're working with like a z equals negative 2, then you want your z obtained to be less than z equals negative 2. So negative 2.3 would give you one of those scores, right? Because it's exceedingly rare. So that's why we're getting these criticals. The z-critical is going to let you know where that threshold is, so that if you cross it, then you can make a decision about your data. So here is an example of what's called a one-tailed rejection region. So this is a normal distribution, and in this distribution we have 1 minus alpha. Remember that 1 minus alpha is almost all, or that alpha is almost always 0.5. So what this means is that 1 minus alpha means that of your data, 95% of it is going to, by chance, fall within this range right here. If you were to randomly pick one single participant in this entire population, 95% chance they fall somewhere in here. So what about that other 5%? The other 5% is represented in this tail. And this tail is, and it's an uncommon place to end up, right? It could be the case that you just randomly choose somebody and they do fall within this region, and it's just by chance, right? 1 in 20. But 1 in 20 is pretty rare, right? That's kind of unusual. It's kind of unlikely. So we're also going to say that anything that naturally occurs in this rejection region, we are willing to consider as possibly significant or possibly not belonging to this population at all, but belonging to a separate population that we have not yet considered. So in the example of like thinking about the audio file, right? So the audio file example that I was working with earlier, this would be an example of like if I am predicting specifically that she's going to do better than 50%, that would make it a one-tail test. I'm no longer interested in what happens if it's worse than chance, yeah, so what this means then is that 95% is here, 5% is here. The reason I'm emphasizing that is because there's going to be other cases like this where you can flip the rejection region or even have it on both sides, and this is actually the most common one, so we'll get to that in a second. But so where does this Z critical come from? What is the critical value here? We want to find a value which is going to cut off the 95% on this side versus the 5% on this side. And what that value is 1.645. So in other words, if you have this as your hypothesis, and you find that the values that you get from data collection, that those Z-scores are higher than 1.645, then you can successfully reject that hypothesis. Yeah. And if we wanted to look at the bottom 5%, then we would just turn this into a negative, and it's totally fine. So I'm going to flip over to my Z-score calculator here. So if I come in here and I'm looking at our probability here, I can even try this 0.05, and I calculate that. Sorry. So whenever I put in 0.05, I'm just trying to find, what part of, resides in just one tail, 5%. I need a z-score of 1.645, and because I'm looking at the lower end, it's negative. If I was plugging that into the higher end up here, if it's greater than that, you'll see now it's positive, and that's reflected right here. So to play around with the Z calculator, because it can help you understand where these Z criticals are. If you get, for example, on an exam, that the alpha is 0.5, and you're trying to find the tails so you can find your Z critical. If it's one-tailed, then you can put it in either one of these, and that'll tell you what you need to know. That's what we just did. But sometimes you might have a two-tailed test. So what do you do for a two-tailed test? Let's see if we can find out. We want to try to find, well, what happens if it's in both of these, in one of these tails? So ultimately, we have to be a little bit tricky here. We're going to put 0.5 here, 0.05 here. I'm going to calculate that. And now you see that the z-score is different. The z-score here is 1.96. Why is it different? Because now we're taking that 5% alpha and we're going to split it up into 2.5. So we have 2.5% over on the left tail, 2.5% on the right tail. And so when we do a two-tailed or a bidirectional hypothesis test, that is the z-critical that we're going to be using, is 1.96. Basically, we need our z obtained to exceed positive 1.96, or that our z obtained to be lower than negative 1.96. All right. So this is just the opposite. So this is just negative, right? But it's the same idea. The same idea applies here. This is, like I mentioned, a bidirectional test, and we're going to see this more often throughout the semester. So we would see this as, the the null hypothesis here would be that the population responses would not be, that they would be equal to 10. And in order to disprove that, I would need to have a z-score that is above positive 1.96, because that's where any z-score right here is 1.96, and any z-score over here would be negative 1.96. So if you ever see in your book, for example, your book will play around with other alpha values. Usually for exams, I try to stick with just 0.05 because that's the value you're going to see in every science. Pretty much every science relies on 0.05. If you're really confident in your results, you can put that to 0.01 or lower. But for the most part, 0.05 is the community kind of, or the industry standard here. So if I wanted to have a different alpha value, if it's not 0.05, what would I do? Let's say it's 0.1, if that's what we want to do. Then we would just throw in 0.1 right here. Whoops, 0.1. That changes it a little bit. And now you can see that, hey, wait a second, it's 1.645. Why is it 1.645? Well, I put it in right here, which means that 10% of our data are going to fall in the tails here, right? And again, that means that 5% is over here in this tail and 5% is over here in this tail, which is why if I wanted to, I could put 0.1 over here in one of these unidirectional tails, and that that did not give me what I wanted, which is fine, or what I thought, because I didn't think this through. That 0.1, when I'm putting it in here, is essentially making this easier to reach that threshold. So the z-score is going to be closer to 0. The closer it gets to 0, the easier it is to reject. So if you have a 0.1 alpha value, that means that you're more likely to reject the null. Anything less than 0.05, the lower it gets, the harder it's going to be to reject that null hypothesis. All right, so the final thing that we're going to talk about before I give you an example is the p-value. So the p-value is essentially kind of, it's related to your alpha value. Your alpha value is that's kind of like your threshold, right? And normally we define that as 0.05. The p-value is going to be what is the likelihood of your data happening by chance. So we are essentially looking for whether or not p is going to be less than 0.05 or greater than 0.05. This is why, and sometimes you hear people talk about like, oh, I hope I get a p-value less than 0.05. It means I have significant results. This is where that comes from. So if we have a p that is less than 0.05, so if we find that our data are, going to occur 1% by chance, that is less than 0.05 or 5%. So we can reject the null hypothesis. We have established that it is significantly or sufficiently a low probability, is sufficiently unlikely. And so we can reject the null hypothesis. If we find that our p-value is greater than that, so if it's 6% compared to 5%, then we fail to reject the null hypothesis. We're not going to say that we disprove the null hypothesis, because technically, you may remember from Research Methods 1 that really what we're looking for is, do we have enough evidence to disprove an idea, to disprove a hypothesis? We can't really reaffirm or confirm a null hypothesis. Logic just doesn't work that way. But this is why we see people talk about significant effects, is because they have found a p-value less than their alpha. So let's walk through an example. And this framework right here, we're going to be doing all for the rest of the semester. This comes from the textbook, so you'll see them all. The textbook also uses this format. So anytime we are given a problem, we're going to state what the hypotheses are. We're going to find the critical values. We're going to find the test statistics, which in our case is going to be a z obtained, but in other cases might be a t-score, an r-score, or an f-score, which is why I'm calling it the test statistic and not just compute the z obtained. And then we are going to make a decision about whether or not we should reject the null hypothesis. So let's say I wanted to come up with a very relatable example, so I'm using drinking water. So it is recommended that we drink 8 glasses of water a day. Do you normally drink 8 glasses of water a day? So that is a testable question. Do you normally drink 8, or do most people drink 8 hours of water? 8 glasses of water a day. So to solve this question, here's a little bit of some context here. So let's imagine that the population on average is going to drink 8 glasses of water a day with a standard deviation of 1 glass. You and your friends are going to record your daily hydration levels. It's going to for 25 days, and you're going to find that on average you drink 7.75 glasses of water. So this is a little bit tricky because what I'm saying here is that I already know the population's characteristics. So if I'm writing that out, I'm going to put mu is going to be equal to 8, the standard deviation is going to be equal to 1, and my x bar, so my mean, is going to be 7.75. So those are the three important things. You may remember that I said, the three things we need to know is what do you expect? We expected 8. That's our null hypothesis. What did you get? We got 7.75. And what is our measurement of variability? That's going to be our standard deviation, which is 1. Okay. There's a couple of other things that are important here, but we'll figure those out as we move forward. So, how do we know whether or not you and your friends actually drink 8 glasses of water a day? Because instinctually, and this is what we've been trained ever since kindergarten, is that we look at these two numbers and we compare them, which is a fine instinct. But in stats, we can't assume that these numbers are always going to be these numbers. It's very likely that if we were to go back and recollect this data, that 7.75 may be different. Maybe next time I collect, I asked my same friends over 25 days, maybe it's 8.5 or maybe it's 10, right? It could change because there's variability. So we have to account for that variability, which is why we are looking at the standard deviation here. So ultimately, we can't just eyeball it. We can't, because I get this every time I teach stats. Some people will say, yes, these two are different. How are they different? Because 8 is greater than 7.75. That's not exactly what we're asking. We're asking is 8 greater than 7.75 when you factor in variability? That we don't know. We're going to find that out though. So, step 1. We want to state the hypotheses. So we didn't specify that we thought that maybe us and our friends are underhydrated or overhydrated, which means that we're going to be using a two-tailed test. So we don't know. So that means that our alternative hypothesis, which is oftentimes where I like to start with these word problems, because usually the word problem is going to give you what the prediction is. So I didn't notice anything about predicting it to be more or less. So then I'm going to say that the alternative hypothesis is bidirectional. So it's not equal to, right? We're saying it's okay if it's greater than, and it's okay if it's less than. We just don't think it's the same as 8. The null hypothesis then is going to be that, on average, the population, including you and your buddies, are going to drink 8 glasses of water a day. So now the next part is to find the critical values. Now the critical values, I'm going to suggest that you should always check the Z calculator, just in case. But you're going to find that there are some values that you're going to see over and over, and this is one of them, the Z critical of 1.96. That's always going to be for a two-tailed test. Two-tailed test with an alpha value of 0.5. That is always going to give you a Z critical of 1.96. If it was one directional, it would be 1.64. But because this is bidirectional, that gives us our Z critical value. The only other thing I want to mention about that specifically is that you can see this is really close to 2, right? It's really close to 2. If we round it up, it would be 2. And if we think back to the empirical rule that we learned in the past 2 chapters, that makes sense, right? Because we talked about how, with 1 standard deviation above and below, it's about 67% of the data falls there. With 2, it's about 96% of the data, right? Which is why we're not exactly doing a Z-score of 2, but we're getting close. So that means that we're going to have, 5% is going to occupy here and here, which means that this is 2.5% of the data, and this is also 2.5% of the data. But this middle part is still the same. It's still 95% of the data. All right, then the third step here is calculating the tests. I have such a hard time saying this. Test statistic. Okay, so how do we do that? You can see here that I'm using a z-score, but I'm using a z-score for a sampling distribution. Why am I using it for a sampling distribution? Because what you're seeing here for a sampling distribution is referring back to this, that you'll note that I'm saying that I'm doing this by asking me and a couple of other friends. So we know that I'm getting a sample and that I'm getting a mean of that sample here, which is why we're using this particular equation or formula. So I'm going to add these in now. So I'm going to add in what I got, which was 7.75, what I expected, which is 8.0, and then I'm going to divide that by the standard error. The standard error, I already know this, the standard deviation, which is 1, but now I'm going to divide it by the total number of samples that I collected. You may have seen, you may remember that that was 25. It was 25 separate days that I did that. So I'm going to get the square root of that now, and that's going to give me negative 0.25 divided by 0.2, because when I divide that up, it's going to be 1 divided by 5, right, which is just 0.2. And then that is going to be equal to, when I divide that up, it's going to be equal to 7 equals negative 1.25. So that is our Z obtained. And if you remember, our Z critical was plus and minus 1.96. So now you should ask yourself, is this value, does it exceed one of your Z criticals? It does not, which takes us to step 4, make a decision. So 1.25 is not lower than 1.96. So that means that we cannot reject the null hypothesis, which means that our hydration levels do not differ from the population. Even though 7.75 is a little bit below 8, what we are saying is that whenever you actually count the variability that all of us experience in drinking water, there is no difference there. That we don't drink more or less than any other population here. So we are going to, and so the way that we would write this in APA format would look something like this. And I'm stressing APA format because in Research Methods 2, you're going to be expected to write it exactly like this, or else it'll be wrong. So we would say that we reject the null hypothesis. Based on the sample of 25 days, we can conclude that the average daily water intake, and then in parentheses, we have what that value is not different than the average water intake. And then I have my stats here. Z equals to negative 1.25, comma, P greater than 0.05. If this were lower, so let's say I had negative 7.25, that would be lower than my Z critical of negative 1.96, and so I would say that we can conclude that the average daily water intake is different than the average water intake. And I would put, Z equals negative 7.25, P is less than 0.05. So you don't need the actual p-value for this class to be put here, because in every situation, that's always calculated by JASP. It's not something that you have to do by hand ever in I was going to say in the 21st century. You don't have to do that by hand. So we just say it's either less than or greater than the alpha value. And the alpha value here was 0.05. All right. One of the final things that I want to mention is effect sizes. Effect sizes, we're always going to talk about this at the very end after we kind of analyze the results here. The effect size is a way of talking about how meaningful our data are. So if p-values are talking about how likely, these things are to occur, the effect size is how important is it. So the most common way to do that for the next few chapters is going to be with what's called Cohen's d. Cohen's d is an effect size measure, and it's something that a lot of psychology journals are requiring you do these days. Like before, you could just get by with using a p-value. Now you actually have to use the effect size. So what this means, or how we're going to do this, is that we are going to take our sample mean. We're going to we're going to subtract that from the population mean, and then divide that by standard deviation. So the only thing that's different from a z-score compared to the previous example is that we're not looking at the standard error. We're just looking at basically we're calculating a z-score. Don't tell anybody that's what we're doing, but that's what we're doing. But this will tell us how far away is our results in standard deviations. So if you have a Cohen's d of 2, basically that means that your group created a shift of 2 whole standard deviations in the data. So for us, we would plug in 7.75 here, subtract that from 8, divide that by 1, which would give us, what, 0.25 divided by 1, so it's just 0.25. Not a huge effect size, as you can see here, the way to gauge these. So we know it's just a tiny bit bigger than a small effect size. So we could say, you know, that, well, actually, I was going to say this is only really interpretable in a meaningful way if you do have significant results, and we didn't have significant results. But if we did, then what we would say is like that this means that your group drinks that much more than the population, about 0.25 standard deviations more. So it is impossible to have a really small p-value and a very small effect size, but it's also possible to have a very small p-value with a very large effect size. They're not always completely related like that, so it's okay if those things do look different. Alright, and then the final thing are talking about error values, or types of errors. So when we are judging a hypothesis, there are two types of errors that we can make. So what you're looking at, and I've never liked the way that this is expressed because it always confused me, but think about this as like, so this is the real truth of the null hypothesis. So is it true, you know, like setting aside the stats, is the null hypothesis actually true? And this is what we do with the hypothesis based on our sample. So this is like, what decision do we make, and is it true or not? So if we retain the null hypothesis, we say that we can't reject the null hypothesis, and it's true, then that's good. If we reject the null hypothesis, and the null hypothesis is in fact false, that's also good. But there are two outcomes that are bad. One is if we reject the null hypothesis, but the null hypothesis was true, so we think that there's a meaningful difference, but in fact there's not. That's called a type 1 error, and that's bad. Yeah, it's just type 1 error. If you keep the null hypothesis, and then later you found out that the null hypothesis was wrong and that it was false, that's a type 2 error, which is also bad, right? Sometimes people call type 1 errors, people will call that the false alarm, which I like. Oh, I don't even know what I was spelling there. I guess I was spelling like F alarm, but false alarm, which means that you think that your results are significant, but they aren't really. And type 2 is that you think that your results are not significant or not important when in fact that they are. A few misconceptions about this. So you may see this on some of the theory-based parts of the quiz and the exam. So the first misconception is the probability value is the probability that the null hypothesis is false. That's not, so the p-value there. So the p-value is the probability that the null hypothesis is false. That's not true. The p-value is just referring to how likely that data are to actually occur by chance. Second misconception, a low probability reflects a large effect size. That's also not true. If your data are really, really consistent, you might have a very low probability, a very low p-value, but a large effect size. And that's fine, but you may also have a low effect size too, especially if you have very, very, very consistent data. And then finally, misconception number 3, a non-significant outcome means that the null hypothesis is true. And I kind of hinted at this earlier. That just means that your null hypothesis can't be proven false yet. So it just means that you don't have the data to prove it false. So that's why we talk about either retaining the null hypothesis or failing to reject the null hypothesis. Hold on. Those sounded very similar. What I mean to say is that that's why we reject the null hypothesis or why we fail to reject the null hypothesis. We will never say that the null hypothesis is true or that we accept the null hypothesis. We are just going to either reject it or fail to reject it because we're just saying we don't have enough data to prove it false. And that is it. I know this was a complicated chapter, so feel free to check out the third video that I'm going to make, which is going to walk you through another example that I'm going to create from scratch, show you how to do it all, like from scratch. But if you have any questions, feel free to email me and let me know what questions you have, or if you want to meet and we can talk about it. Yeah. So I'll see you in the third video where we will walk through an example of this. Thanks for tuning in. I'll see you later. Bye.